Hey everyone, welcome back to the channel. So in today's video, I'm going to be showing you the Lin method on Square-1. This is a tutorial and it's finally out, so let's get right into it. So before I actually dive into how the Lin method is used to solve the Square-1, which is this wonky looking puzzle, let me talk about scrambling and notation because those are a little more important. So first of all, for notation, you'll often see scrambles that look like this, and all that this is telling you is you'll have parentheses which have two numbers. They look like coordinates but they're not, and you also have these front slashes. So the parentheses refer to the numbers, the number of moves, or like how much you need to turn the top and bottom layers respectively. And if it's a positive number, it's a clockwise direction. So this is clockwise for the top layer, this is clockwise for the bottom layer. And if it's a negative, then, vice versa. So for example, if you have something like 3, 0, the way you would do that is each of these inner pieces is an edge piece and each of these is a corner piece. So each edge piece is worth 1 unit and each corner piece is 2 units. So 3, 0 would be one of these and then one more of these. Right? But now you might ask, well, where do you measure that from? So this is where the middle layer comes into play. You'll notice the middle layer just has 2 blocks. So what you want to do is keep one of the wider sides of the blocks on your right, if you're a righty. If you're a lefty, you could do everything I tell you in this video with the left, but usually people just do it on the right. So keep a wider block, like this is wide, this is narrow. Here you'll just see like this is the side of the block, this is wide. So you could also do everything I tell you in this video from this orientation. I just prefer this orientation. So this layer can only go, or this along this axis, layers can only move this way. And this particular line that runs throughout the entire Square-1 is called the slice. Well, you'll see in scrambles you'll have slices between these. This is the slice move. It's a 180-degree rotation about this layer. So 3, 0 would be starting with this line as your reference, 1 plus 2, that's 3, and then slice would be that, and then you keep going. So as another example, if you have -3 and -4, it would be something like this. So negative is counterclockwise, that's 2 plus 1, that's 3, and then here is counterclockwise as well, so 1 plus 2 plus 1. So that's all of those pieces, that's 4, and then you would slice. So now that that's out of the way, you know how to read Square-1 notation and you know how to scramble the Square-1, so let's get into this video. So here's the scramble Square-1, and just as an overview, here are the steps of the Lin method. So the first step is to make a cube shape. Which is something like this, for simplicity, something like this. So now the shape of the Square-1 is a cube. The second step is to make 2 blocks, which look something like that on each side. The third step is to solve the back edge. In this case, it's also going to solve my front edge, so I'm just going to change that a bit. Yes, after you solve the back edge, the fourth step is called CP plus DF, which permutes the corner, so corner permutation of your top layer, and also solves the DF edge, which is this down front edge. And you basically have a few cases for this. So that's all that, and the corners have been permuted. And the fifth step is just an EPLL. In this case, in this particular video, I'm not going to be showing you any advanced algorithms for EPLL, but you could learn all the EPLL algorithms. I'll just be showing you the basic U perms, the H perm, and the C perm, and parity, of course. And that's it. Your Square-1 should be solved by the end of that. So feel free to use the video chapters to skip around to any step that you want to see in particular or that you already know. So let's get right into the first step, which is cube shape. Now, in order to get your Square-1 to a cube shape, you need to understand how the pieces work. Remember what were edge pieces and corner pieces? Well, we're going to use those to basically build the cube shape up from the bottom. The goal of cube shape is for you to get all 8 of your edges onto the top or bottom face, preferably the top because it's just simpler to navigate. And every one of your remaining corners can be, across the puzzle. Let's try pairing corners. So again, keep the wide block on your right at all times through the solve. And for example, I see this pair of 2 pieces and I'm just going to, actually, you know what, I can just take this here and get all 4 of these up here. And now you'll notice that all 8 of my edges are on top, 7 here and 1 here. But this is not ideal because I want all of them to be together, so you can do this magical thing which I will show you after this. But in order to do that, you need all 8 to be together, so you basically need this edge to pair up with all 7 of these. And in this particular case, this is like the worst possible case you can get for that. There are other cases where you can keep pairing 1 or 2 edges at a time to build the 8, but in this case, what I would do is keep 6 of the edges that you have made on the left and take this L effectively and break it. So now that you've broken it, move these 6 out here to where you have 4 on the left, 2 on the right, and replace the L with this pair. So now you should have 5 plus 1 and a pair down here. And then take this pair and replace this wide line with that pair. And then take the wide line, shift all 6 to the left, put them up. So this is obviously not the best way to do it. It's just the most intuitive way to do it, the way you should break the pieces and then repair them so that you don't have an L which is adjacent edges, but a line which is opposite edges. And then you have all 8 of these edges, 2 corners and 6 corners on the bottom. This exact orientation of corners and edges is what you're aiming to have. Once you have this orientation, it's very simple. Take the 8 and break them into 4. Then again, remember I'm always keeping the white thing on the right. Of course here you might notice it's not, but when you move it, you will see that it's on the right. So anyway, take the 8, break them into 4. Then take each of the 4s, align them, perfectly aligned, break them into 2s. Then take each of the 2s, but now misalign them and break them. And now you get this shape, which is a very, very commonly known shape called a kite. So you have one kite here and a kite here. Align the kites with their tails. This is a kite, just for, think of it as you're flying a kite from there. Align the kites and slice. And now you should have a square on top and a square on the bottom. This is cube shape. But now you might ask the question, why is this not solved? What is up? What's happening here? But just remember that this is similar to this on the 3x3. So when you have something like this, everything's pretty much oriented and looks correct, but these two are swapped and these two are swapped. And exactly how you would solve those, which is just R2, U2, R2, U2, R2, U2. That's exactly how you would solve this. It's effectively like slice, 6, 0, slice, 6, 0, slice. That solves it. But do remember, this doesn't really matter. Like, it doesn't matter to have this block like this because the rest of the cube determines the cube shape. It's not the block. But yeah, anyway, I'm going to, for simplicity's sake, just keep that solved. So yeah. That is your first step done. So let me show you one more example of a cube shape. If you're confident with cube shape, just skip to the next part. So here's another example of the cube shape. Again, remember, this is not the best way to do it. It's just another way to do it. The first thing I would see here is like, okay, I have this shape on the bottom, this shape on the top. Also just note that this is called a kite. Remember the kite thing, but it doesn't matter. There's many different shapes. You should go check out this video where I talk about how a speedcuber solves the Square-1 to see the different shapes that exist. So I see this line for the kite and I do see this line as well. So what I'm going to try to do here is pair those lines, because I know that when you put two lines next to each other, you get a pair on top and a pair on the bottom, just like this. And I have two pairs here. Now all my pieces are effectively paired. I just have to align all of them. So I'm going to take these two and align them with these. So that's 4. Then I need to make sure these two are aligned. So what I'm going to do here is I'm going to take these two, throw them up there. That's 6. Then I'm going to take these two and also throw them up there, and that's 8. So again, like, don't get scared by what's happening here. It's more or less just pair edges, put them on the left because you're only moving the right when you do a slice. Put them on the left, swipe more up, push them to the left, put more up. That's pretty much, you just keep doing that process. And in the case that you don't get something that's already paired, like you get an L, you remember what to do. And if you get a line, you know what to do. So try to make the L into a line and then solve it. So yeah, once you get the 8, again, split into 4s, align the 4s, split into 2s, misalign the 2s, which means 2 here and the 2 here instead of here. Do that, you get 2 kites, align the kites, and you're done. So that's pretty much it. Again, I'm just going to fix this, you don't have to. And that is cube shape done. So congratulations, if you've made it this far, you now have the shape of a cube. It represents any of your other cubes. Now the next step is very similar to the roux method on 3x3. I will link the video up here. It's not my tutorial, but it's a roux tutorial that's pretty good. So in roux, what we do is, unlike CFOP where you do the cross, in roux you kind of solve these two opposite bars. Please forgive me because I don't use roux, but effectively what I'm saying is, like, I make this bar first, this any one of the edges, and then I make the opposite block. I should say block instead of bar, but that's effectively how you do bars on roux. Very, very poorly done, but just for demonstration's sake. So this is what we're aiming for with the Square-1 Lin method as well. So you want to make 2 blocks like this. Now, a very, very useful trick to make any of these blocks is to look at corners and edges, because at the end of the day, blocks are just combinations of 2 corners and 1 edge, right? So let's see what we can do. The first thing I notice is well, remember that you have the freedom to make any block. So I just see the blue corners here, and I know they're already together. Even if they're not, you can always do the same thing. Put anything you want to stay up there just on the left, and then bring the other one to the right. So here, I'm going to take these blue edges, blue corners, I'm going to put them down here. So what I'm going to do is move it here and move it down. But you might have noticed that destroyed the shape of the cube. Why is that? Well, that's because that's how the Square-1's designed. This cut is not symmetric, it goes like this. So over here it's a left slanting cut, but here you'll see it's a right slanting cut. So doing that will change the shape of both. What you want to do is you want to misalign one of the layers a little bit, so that when you do that, like, you will get a case where it remains a cube. Now in this particular case, I just want the corners and not this edge, so I won't misalign the top layer because you will notice that gets even the edge down. I will just misalign the bottom layer, get the corners down, and then now you'll see I have the corners here and the other edge is here. Now is the trick that comes into play a lot in solving a Square-1. It's called an M2. So in the 3x3, an M2 is just this, right? But it's not as simple in the Square-1, because the same goal of achieving an M2 in the 3x3 by swapping these two edges and these two edges, and all the centers of course, is not achieved by just doing this on the Square-1, because you're also moving this corner. So the way you do an M2 on a Square-1 is very simple. This is the algorithm. It's 1 0 slice -1 -1 slice 0 1. And this might seem very weird, but it has a really neat finger trick. So you can push for the 1 0, slice, pull both for the negative moves, slice back, and then 0 1. So that's how easy it is. And that, you will see, has basically got this edge down here, and I've made a bar. I can now put the bar on the left. Again, anything you solve, just put it on the left. That is how the Square-1 works. So that's the bar done. Now what's the opposite to blue? It's green. So next thing I need to do is make a green bar. Now let's look at the corners. First corner is here, second corner is here, and the edge is here. Remember, this is not the best way to do these bars. Again, this is just the most intuitive way. This is just a tutorial. So I will first try to arrange the corners. So let's see. I want to keep this green-orange corner here. Let's move this green-red corner around to see where it can make a nice pair with that. So let's first... Now remember, if I do this and move it, well, there's no harm done. So you can misalign either of the layers at this point, because your corners are just far apart and not connected to the edge in any way. I just prefer misaligning the top layer because I have this solved. It's not going to affect it anyway, but yeah. So I'm just going to move this down. Then I'm going to move this over. Let's see. So now I've done this. Now they're opposite to each other, but this is good. Like, this is now one step closer. This was all here. Now it's here. So if I do the same thing now, hide this, get this over and get this back. There you go. The corners are now together and the edge is here. So can you think of a way to now move this edge here without disturbing anything else? So it may not be very obvious, but you can use the M2 to your advantage. Since nothing else is solved, I can do an M2 and put this here, and then do a U2 to put these corners back there, and then do another M2. Like so. That's there, the M2 is done, U2, and M2. And that's it, it's a pair. That's it, it's that simple. And then similarly, just put it back down there. Remember, if at any point you find your cube to be away from the cube shape orientation, you've made a mistake of not misaligning the layers before making a slice move, and that's very common, so don't worry about it. But yeah, with that M2, the green bar is done, and I finished blue and I finished green. Hooray. You will notice so far we don't have any algorithms whatsoever, and this is where the Lin method is so nice to learn, because you don't really need any algorithms, except for the M2, which is just an intuitive way to do the M2 cycle. Then, after this, the next step is to solve the back edge, the DB edge. And in this case, that's the orange edge. Of course, you could just do this and say it's the red edge, but the red edge is here. I don't really want to do any of that. So the orange edge needs to go back there. How would you move the orange edge back there? You might have guessed it. It's an M2. So just do 1 0 slice, -1 -1 slice, 0 1. That solves the DB edge. And now we are finally at the closing stages of the solve, because you will see a lot of it is solved. The second last thing to do is CP plus DF, which is what I talked about, where you permute the corners of the top layer and solve the DF edge on the bottom layer. And there are 6 total cases for this stage, and I will be going through all 6 of the algorithms you will need to solve this. So do bear in mind, these might be a little weird at in like initially, but you will definitely get used to them. And I also recommend just doing more solves and learning more Cubeshape cases so you'll get better at it. I'll leave some resources in the description below. The first thing you need to remember is that anytime you're solving CP plus DF, you want to keep the unoriented edge on the left, always on the left. And the DF is just in DF, the position down front, which is corresponding to this, is always here. This orientation you need to maintain so you can identify the cases easier. So in this case, I see this bar on the front, but that's useful. So what I'm looking for is not actually a bar, it's just headlights. You might have heard of headlights in cases like this, where you'll see two corners that are solved, but on the same face, and no other such corners. So headlights are a way of recognizing what case you have. In this case, by doing CP plus DF with the edge on the left, you will always have headlights on either the front, the left, the back, the side, all of them or none of them, which is where the 6 cases come from. So now it should make sense to you. So let's go through the cases one at a time. So the first case is a case like this, where the bar is on the front. Let me not say bar, let me say headlights. The headlights are on the front, because you're not always going to have a bar, I just got lucky. So the headlights are on the front with this on the left. The algorithm for this case goes like this. And just like that, DF is solved and so is CP. This is the state I had it in. I just did a U prime to align that. But yeah, again, I shouldn't say U prime, it's technically a -3,0, but yeah. That is CP plus DF done. But okay, that was only the front headlight case. So let's go to the next one, which is the left headlight case. So here's a case where the DF edge is unsolved and it's the unoriented edge is on the left, and now the headlights are on the left. So if it's on the left, you should do this algorithm. That's it. And CP is done with DF solved. So let's go to the next case, which is the back headlights. So here's a case where again CPDF and we have the headlights on the back. In this case, you should do this algorithm. That's it. That's CPDF done. Now the next case, which is the headlights on the right. Again, here you have these headlights are on the right, and you should do this algorithm. That's it. So as you can see, these algorithms, I'm doing them a little quickly, but the point is you have them all on the top, so you can just refer to them at any point. They'll also be in the description. So next, let's move to the case where there's only headlights. So a case where there's only headlights looks something like this. Again, the back is solved, and then you have this unsolved, the thing on the left. In this case, it doesn't matter where you put the unsolved or the unoriented edge because headlights are everywhere. In this case, in fact, we want the opposite of what we usually have. So you want to set it up where the DB edge is unsolved, and instead of the unoriented edge on the left, you want to put it on the right, and then you want to do this algorithm. So again, pretty simple. And finally, the case with no headlights. So here's a case where again, you just have CP and DF, but you will see absolutely no headlights. So in this case, what you want to do is maintain the same orientation and do this algorithm. That's it, and that solves your CP. So with that done, you are now at the final step of your Square-1 solve, which is EPLL. So there's a couple of things here. Either you could get parity or you could get no parity, but this particular case, as you will notice, we don't have parity because this is a possible case on the 3x3 as well. Looks something like this, and you can see it's just completely identical to the 3x3. In any case, for the EPLL, which is just a permutation of the edges of the last layer, I will just go over the 4 most important cases that you can use with every other case. So the first one is literally this, it's a U-perm, but in this case it's a U-A-perm because it's a clockwise cycle of the edges. Before getting into the algorithm for that, you should notice why it's a clockwise cycle, because green's going here, red's going here, blue's going there, that's clockwise. You want to keep the bar facing U and the opposite colored thing on the right. You should do something like this. And that's it. That solves that U-perm. And also notice the Square-1 is now solved. But anyway, let's do the other U-perm. So the other U-perm is the exact same thing, but the opposite cycle, so counterclockwise. And for this, you want to again keep the solved side facing U and do this algorithm. And that's it. That solves that U-perm. Now we go into the more intuitive permutations of the last layer edges, which are the H-perm and the Z-perm. So the first thing to notice is that the H-perm is completely analogous to that of the 3x3, but it's not the same algorithm. In fact, you will like the H-perm alg for the Square-1 a lot more because it's entirely intuitive. So if you can guess, the tool that we've been using so far for things that we don't really know what to do for is the M2. In this case, you should use the M2 because you'll notice these are all opposite swaps. It's just two opposite swaps, right? It's either cycles or swaps for the last layer, and in this case, you have two opposite swaps. So when you have two such opposite swaps, you can just do an M2 from here, which would get these here, then do a U prime, an M2 for these, which would put those back in these, but get these here. Then do a U2 because these are now here, and you want to replace them with their opposite orientation, hence the U2, and then go back to this one's opposite orientation and replace that. So it's a very, very intuitive thing. So watch this. These two, I'm going to do an M2. Then I'm going to move it to the right or the left, totally up to you. And I'm going to send those two pieces back into these slots just because I want to get these two out. So another M2. And remember the pieces that we just got out were oppositely oriented. So now you will do a U2 effectively. And then I'll do another M2 because now those are in the right spots, as you can see. And then I will go to the last possible orientation and do an M2. That's it. That's the H-perm. And very similarly, the Z-perm is... Well, if you could catch that, then you know what I just did. But it's almost the same thing. Now, instead of the swaps being opposite to each other, they're adjacent to each other. So you want this blue to go here, this red to come here. So, yep, you guessed it, M2. So do an M2 from here. That'll get this blue down here. Get the slot where it has to go over. Do an M2. Get the slot back. Do an M2. So to put it into like notation, I won't put it in exact Square-1 notation because it's easier to just remember it as a normal thing. The H-perm is just M2, U or U prime, M2, U2, M2, U, well, U prime or U, M2. And the Z-perm is just M2, U prime, M2, U, M2. Remember, I'm doing U prime because I need to go there. If you were doing this alg from this angle, you would do M2, U, M2, U prime, M2. So yeah, you get the intuition, you can solve it. So that covers all of the EPLLs you need to know, but have you ever seen this on a Square-1? Now you might be wondering, why am I just showing you a solved Square-1? What's wrong with me? Well, psych.
That's the wrong number!
It's not. This is possible. This happens on a lot of even ordered n by n's as well. But this is called parity, as you might have heard of, and you will never have a case like this on the 3x3, because on the 3x3, if you have these two swapped like this, you will always have the back swapped as well. That's just how group theory works. So to take that to Square-1, an odd number of swaps is always going to be parity, and an even number of swaps is always never parity. Why did I say always never? Anyway, it's never parity. So the algorithm for parity might be the only annoying algorithm in all of Square-1 or in the history of cubing. So I do apologize for this algorithm's length and well, just how bad it is. So here's the algorithm I use for parity. You want to keep the swapped edges in front of you and do this. Now that solves the parity, but it did flip this bar. Do you remember how we solved this bar? Yes, it was an R2, U2, R2, U2, R2. So it's like R2, U2, R2, U2, R2. Which goes to say that the parity algorithm that I just did actually solves, in technicality, it solves this case, and not the one with the bar entirely solved like this. So if you get something, that's why I say like just leave this to the end, because if you have parity, it'll just cancel out with the algorithm that you do for parity. So yeah, now you have all the tools you need to solve the Square-1, but let me give you a quick test. What would you do in this case? So in this case, you might notice, well, it just looks weird. It doesn't look like any PLL you've seen. In fact, this is a completely counterclockwise cycle of every edge. It's called an O-perm on Square-1. But anyway, let's not get into the algorithm for the O-perm. There are algorithms for the O-perms, both counterclockwise and clockwise, and the W-perms, which are permutations like that. Which again, you don't need to know them, but how would you solve this? Is there an intuitive way to approach this? Well, one thing you might think of is that, you know, these are all going in a counterclockwise cycle. So if you try doing a counterclockwise cycle, which is a UB perm, it might solve something. Well, it will solve something. In fact, it will solve these three edges, right? Because this will go here, and this will come here. And then red and green will be the parity case I just showed you. So I hope you understand why I showed you this test. It's because, well, every single case that you don't recognize is a combination of parity with a non-parity alg. So in this case, we're just going to do the counterclockwise U-perm. And as expected, we get parity on the front. That's it. That is the end of the tutorial. That's all the tools you need to solve a Square-1. So again, just a quick recap. Cubeshape, use smart edge pairing and try to get all 8 edges to be paired together. If you have any kind of adjacent L cases, try to convert them to line cases by breaking pieces smartly. I did say a lot of vague things there, but I showed you how it was done. You can rewind the video to go check that. Then you have the 2 blocks, which are the most intuitive step by far. Try solving the corners first and then the edge remaining. It's not the best way to do it. I will repeat that. It's not the most efficient way, but it is the easiest way to understand. So try doing that, get a block on the left and get a block on the right. Remember, if you ever solve something on the Square-1, move it to your left away from the wide block of the Square-1. Put it on this layer because you're just never going to move that layer. So just put it on that layer. Then you get to solving the DB edge, which is at the back. Very simple, just use M2. M2 was used in the block building. M2 is used in the DB step. Then you get the CP plus DF step, where you have to solve the DF with permuting the corners. That as well is very straightforward. You just have 6 algorithms you need to know, and they can solve any case, any possible case. Once you're done with that, you will have just the permutation of the edges of the top layer, for which we discussed the U-perms, both of them, clockwise and counterclockwise. We discussed the H-perm and the Z-perm. That's all you need to know, plus parity, which I just showed you. Any case you don't recognize is a combination of a non-parity and a parity alg, and all you have to do is test, like just experiment with it. You will figure out which case is what. You can also learn the algs for those special cases. I will leave all the resources I have in the description. And yeah, that's all for the tutorial. So please leave your feedback in the comments and any questions you may or may not have. Actually, if you don't have questions, I don't know what you would leave in the comments. Just leave something nice, like a heart or something. But yeah, that's pretty much it for this video. And remember, keep learning new stuff. Learn more Cubeshape algs. It'll be really helpful. There's some very, very nice cases on Cubeshape that always simplify very easily. One of them that I can tell you straight off the top of my head is called Scallop Kite, which is a very easy case to solve. But yeah, anyway, let me not get into all that. And yeah, just keep in mind that this is an intuitive method until you get to CP plus DF, that weird step, where you learn 6 algs and then you get to the last step, which you'll only learn 2 algs, technically the U-perms, the H and Z-perms are intuitive, and then you learn parity. So you're learning 9 algs in total, and you know the entire Square-1. Like, you don't need any algorithms for anything else. So yeah, thank you so much for watching this video, and I will see you in the next one. Take care and peace.